is similar to what we heard today about in other contexts, dark energy, for example. And it is that when people speak of evidence for dark matter, this isn't really what they mean. They mean that there is evidence for a problem. So there's evidence for dark matter only if you believe in standard dynamics, quantum dynamics or general relativity. But if you permit yourself deviations from this theory, it may well be that you can explain all the observations that have led to the requirement of dark matter. You can explain them in a different way without needing dark matter. So time, of course, doesn't permit me to give a review of what's been done in these 30 years, but so I decided to concentrate on two aspects. I'll talk a little bit about phenomenology, what MOND predicts very generally without even specifying the exact theory, and then I'll jump and discuss a recent, relatively recent new relativistic theory of MOND. Okay, so what is MOND essentially? It hinges on the fact that the accelerations you find in galactic systems are many orders of magnitude smaller than what you encounter in the solar system. So you may easily or conceptually at least devise a theory that gives you, coincides with standard dynamics in the solar system. So you get the same success of standard theory in the solar system, and yet gives large departures in galactic systems. And the basic observation is, as I said, led me to hinge the theory on accelerations. So conceptually, in a similar way to what you may think of relativity, for example, you introduce dimensionful quantity with dimensions of acceleration, just as C acts in relativity or H bar acts in quantum mechanics, and it basically delineates the limit of applicability of standard dynamics. So you say, since acceleration in galaxies are very small, the theory should be such that for acceleration much smaller than this constant A0, things behave differently. For acceleration that are much larger than it, we want to restore standard dynamics. Formally, you can say the following, that we are looking for a theory that has in it, or you are allowed to use in the construction of the theory, beside the standard constants, let's say G and the relativistic limit C, you use A0, and you want the theory to be such that in the formal limit, A0 goes to 0, which amounts to saying that all accelerations in the system are much larger than A0. You want to get standard dynamics again. And the crux of the issue is really what you require in the opposite limit. So the opposite limit is when A0 goes to infinity or becomes very large compared with acceleration in the system. Technically, it turns out that you have to require at the same time that G goes to 0, so that G times A0 remain fixed. And then what do we require? And this applies to the non-relativistic regime. We require that the theory becomes scale invariant. Okay, so let's say we want to describe a galaxy or any system of gravitating masses, many masses, and the dynamic theory that describes them should be invariant to just rescaling all times and all distances by the same factor. Now, this is not how the theory was introduced initially, only realized this later on. It's not clear that it has some deeper meaning in the symmetry. It might, but we're not aware of any such deeper meaning, but at least as a mnemonic, you can use it to remember what the MOND theory should look like. Okay, so I'll show in a minute how this comes, how this enters. So, for example, in a very simple case, the very schematic case, you have a point mass, and you have a particle moving in an orbit around it, let's say a circular orbit at the radius r, and you want, in this case, what's the acceleration of this particle as a function, of course, of the central mass. You only have as parameters the mass, g and a0, and the radius that you can use. So just on dimensional grounds, the expression for acceleration has to be that, on top right there. Okay, It's just mg over r squared gives you dimension, then some dimensionless function of the only dimensionless quantity that you can form, which is mg over r squared a naught. So in the limit a naught goes to 0, in other words, the argument of f goes to infinity or becomes very large, compared to 1, you want to restore standard dynamics, so f has to go to 1. In the opposite limit, you want scale invariance. So a being essentially length over time squared scales like 1 over lambda if you scale everything by lambda. M and G not scale. 1 over r squared scales like 1 over lambda, so you want f to scale like lambda, so it has to go like 1 over the square root of its argument, so as to get the r, 1r power on top. So this is what f has to be the limit of small acceleration. So that's how the requirement of symmetry enters dynamic in a more explicit way. So what's the next step? Next step is to construct a theory that will embody these tenets, these basic requirements. And then, well, ideally, you have a theory that you trust, and then you apply it. You go to a galaxy, another galaxy, a set of galaxies, clusters of galaxies. And then you want a relativistic theory, you want to apply it to the universe at large, and so on, to lensing, to cosmology, and everything. So that's the general program. But even before that, it turns out that there is a lot that you can say even before you have an explicit theory, and this can be put in the form of general laws that I've listed here, and I liken them to Kepler's laws because some of them are Kepler's laws, but others are not. Okay, and before I describe one or two or three of them in more detail, I just want to say some general things about them. So, and this is what these laws are characterized by. So in the first place, they essentially follow only from the basic laws on the second transparencies. So they should be shared by all theories that embody these independence. Now, it might seem odd, but in fact it is so. What look like a simple requirements actually lead to very far-reaching consequences. Okay? So this is one thing to remember about this law. So, okay, the basic predictions of MOND follow from only the basic assumptions. So, okay, the second thing is that all these laws are independent. They're independent, for example, in the sense that if you want to interpret them in the context of dark matter, so let's say, some would say, okay, MOND works well, but we're going to understand this one day in terms of dark matter. So it's just that galaxies form in such a way that somehow they obey these rules. The fact that they are independent means that in the context of dark matter, none of them follow from the other. So if I assume that some of them are obeyed, I cannot derive the other consequences. And this is easy to see because you can construct families of galaxies made of dark matter and baryons that will obey any subset of these laws, but not the others. So clearly, in the context of dark matter, they will each require a separate or independent explanation. And essentially, part of this is reflected in that if you translate or if you express these laws in terms of dark matter, it turns out that some of them tell you something about dark matter only, about the properties of, some of them describe properties of the dark matter halos, so to say. Some of them describe properties of only baryons, and some of them describe relation between the baryons and dark matter. Okay, and also another thing to remember that you will see when I go back to that slide, that many of these predictions involve A naught. So testing them permit you to determine A naught in different ways, and they are different and independent ways. Okay, so let's take the first one, for example, which is a sort of quintessential prediction of MOND, and in fact, it was my initial axiom, so to say, in constructing the idea. You can ask me, why do you require scaling variance and so on? So scaling variance immediately gives you asymptotic flatness of rotation curves, and that was my initial building cornerstone for building the sphere. So how does it work? Very simply, what does it mean? Let's say you have some galaxy and you consider particles on orbits around it, let's say circular orbits. So scale invariance means that if you take an orbit that is 10 times larger and you also increase times 10 by a factor of 10, so velocities remain the same, so the orbit is still an orbit. Of course, at the same time, you have to inflate the central mass, but because you are talking about asymptotics, it doesn't make a difference if you increase the volume of that mass a little bit. So asymptotic flatness follows straight away from the requirement of scale invariance. Now, the second prediction tells you how this asymptotic velocity depends on the total mass of the system, of course, baryonic mass. And again, because you only have at your disposal A naught, G, and M to construct the velocity, or the radius if you wish, but the only way to construct it, the only quantity of dimensions of velocity that you can construct for mass G, A naught, and the radius is the fourth root of this, of mg A naught. So inevitably get this relation between mass. And this, of course, is what underlies the different tests that go under the name of Talley-Fisher relations. So, for example, these are two recent such tests, very recent. So here, what is plotted here for a set of many galaxies is the total baryonic mass, and the secret is to include the total baryonic mass, not only stars, but also the gas and everything that you can take into account. And the other secret is to plot it against not just any velocity measure, as is being done in many of Talley-Fisher plots that you see in the literature, but to actually choose for each galaxy the asymptotic velocity from the rotation curve. So you can only use galaxies with rotation curves here. And this is what you get, and the band is the prediction of MOND. The width of the band just reflects uncertainty in the value of A naught. And this is yet another recent test of using a different sample of galaxies. These are galaxies that are dominated by gas. So you may know that the gas mass can be measured directly, whereas the mass in stars, you need to know the conversion factor of mass to light ratio, which we know is in a factor of 2 or so, but still. So this is a more puristic plot. Okay, and this shows you that, so the histogram just reflects the actual scatter of points around the predicted line, and this Gaussian tells you what you would expect from just the measurement errors, and the fact that the two are the same basically tells you that this has no intrinsic, or at least is consistent with no intrinsic scatter. Okay, so there are quite a few of these. So the first one is an example of a prediction that concerns the dark matter halo. Of course, alone, because the asymptotic velocity is something that's determined by the halo. By the time you are in the asymptotic region, baryons contribute hardly anything to the velocity, so this tells you something about the structure of the halo. This tells you something about the relation between the halo and baryons, because this velocity is determined by the halo. These are the baryonic mass. Okay, and there is another prediction. For example, let's take this one. Okay, you may know that so isothermal spheres cannot exist in Newtonian dynamics. In Newtonian dynamics, self-gravitating isothermal spheres have infinite mass, and they do not exist. In MOND, they do exist, and they all have a very interesting property, which is that their mean surface density cannot be larger than A naught over G. Okay, so A naught is acceleration, A naught over G is dimension of surface density, so MOND introduces not only a characteristic acceleration, but a characteristic surface density, which appears in galaxy dynamics in many places. You can see that. Okay, so applying this, for example, to systems like elliptical galaxies, the prediction would be that elliptical galaxies would have a maximum on the surface, on the mean surface density that they can have. And the reason is very simple. If you take an isothermal, to the extent that ellipticals are described by more or less isothermal spheres. So the idea is very simple. If the surface density of an isothermal object is smaller than this, it is in Newtonian. It means that the mean acceleration in it are Newtonian, then it cannot exist as an isothermal sphere. So what it would do, it would just expand until it hits a certain radius where its surface density will become roughly that, and this is where it will stick. Okay, so anyway, these are the predictions. I don't have much time to discuss them, but this is an interesting one discovered only recently. If you can ask yourself, suppose, okay, you take a galaxy, you measure its rotation curve, you deduce the halo properties for this galaxy. MOND predicts that the mean surface density of the halo has a universal value, which is also this roughly, okay, so this is the mean surface density of the halos predicted by MOND, which is A naught over 2 pi g. And this is a recent compilation of such a thing. It was not done to test MOND, it was sort of an independent. In fact, the MOND prediction was discovered after the observation was made. And that is what instigated looking for a MOND prediction for this. Okay, so essentially, this is a set of galaxies for each of which a halo model was determined. In particular, these were halos characterized by co-radius and central density. So what is plotted here is the log of ρ0 times r0, which is a measure of the mean surface density of the halo, and this is what MOND predicts. Okay, so this would be also a pure halo property that is predicted by MOND, also involving A naught. But of course, sort of the flagship of MOND testing and prediction are rotation curves. I'm trying to show you a few, and I want to stress the fact that essentially these are not fits. Okay, so this is data. This is what Newtonian curve is, just from the baryons, and the line going through the data point is the MOND prediction. So it's not certainly in systems that are dominated by gas, even M over L, you don't need to know M over L for the stars, because stars in this case, for example, stars are quite negligible. So you know the mass, you measure directly the mass profile of baryons, and from that you just you predict the rotation curve. There's no fitting. Okay. And more recently, it's been possible to achieve similar force of testing MOND for elliptical galaxies. So this, I just posted it last week on the archive. So essentially, this is what is plotted here is the accumulated mass in different components. So this is the accumulated mass in baryons. This is the deduced accumulated mass in dynamical mass, then this uses X-ray emitting gas around these elliptical galaxies. They go very far, in this case almost 200 kiloparsecs, almost 100 kiloparsecs. And okay, so these are the round points and the gray region are two different estimates of the dynamical mass, and the black squares are what you predict for MOND with no free parameter. And taking this scalar, which is the baryon profile, and just calculating for MOND. Okay, so A naught has been determined from all these different ways, and of course they give consistent results. And the very interesting fact that I have really no time to talk about, but it's already well known, that A naught itself in value is very near a cosmological acceleration. So if we define A bar as 2 pi A0, it's almost exactly equal to within, 10-20% C times H0, and it's also very near, because of this famous cosmic coincidence, this and this are really the same. So it's either it's just a coincidence, or if not, it is telling us something very deep on the origin for MOND. And I should say as a general comment that all COEs that we now have for MOND, I believe are only effective COEs at best. So they are not, we are still looking for deeper and deeper COEs that, among other things, will explain this coincidence. And in the list, you can consider it just another cosmic coincidence, because A naught is there, it's clear. Maybe it's not, some people would say it's not a new physics, but A naught is, so A naught is there in the data in many ways. Okay, so what we see is that this A naught, which appears ubiquitously in galactic dynamics, is also related, at least numerically, to some cosmological constant. Now, this is a time where I skip a lot. So very quickly, it has to be realized that MOND doesn't explain everything. It still has some, I don't know to call it a problem, but things that it doesn't explain. And it's very famous that MOND does not explain away all the dark matter in galaxy clusters. It reduces the discrepancy from a factor of 5 to about a factor of 2. And there is the bullet cluster, but it's just part of the same still missing link. If you want, I can tell you more about this during the discussion. I will not discuss a line of non-relativistic theories that have served us for many years. And the basic idea was that you want to consider MOND the modification of gravity, so modification of the Poisson equation. So let's say in the non-relativistic level, you have this here, A, this is just Newton's second law, A is minus God of the gravitational potential, and potential itself is determined from Poisson's equation here. Now, so you can modify this dynamics, writing a theory that obeys the initial tenets that I described before. So there are several versions of these theories. I will skip description. There's now a respectable line of relativistic theories. There has been relativistic theories from the beginning, but they were rather unsatisfactory. And the first really good one was Teves, that was already mentioned in last talk by Jacob Bekenstein, with some nice properties that I don't have time to discuss. And after that, I think psychologically people realized that it's possible, so they started to look for other theories and came up with a few, in fact. And this is perhaps the most recent, which is dubbed BiMOND for bimetric model. In the time that I've left, I want to discuss it a little bit. So you start, okay, bimetric theories, of course, have a long history, at least since 1970s. And they simply start with two copies of general relativity. So you have spaces endowed with two metrics instead of one. And matter knows only about one. So matter moves essentially on geodesics of one of the metrics. The other one may be considered an auxiliary metric. It may have a deeper role. And then the difference between the theories is actually how you couple the two metrics. Okay, so we have here, this is the general action. The action is just two copies of Einstein-Hilbert action, one for the first metric, let's call it, or our metric, and another, this is for the other metric, the auxiliary metric. There is the matter action, which we take to be the standard matter action, namely all matter degrees of freedom coupled to the metric in the standard way, and coupled to themselves in the standard way electromagnetically, strong forces and so on. Okay. Now, then you may ask, okay, if we add another metric, shouldn't we also add another matter sector? I mean, why should our metric be so privileged to have its matter coupled to it? So it's a logical extension. It's, as we should see, it's not necessary to get MOND, but it's something that it would be good to explore. So in principle, we add also a matter sector for the other metric. And really the crux of the thing is in the interaction. Okay, so this is just more explicit. Einstein-Hilbert for R is the Ricci scalar for our metric, R hat is the Ricci scalar for the other metric. these are the matter actions, and this is the interaction. Now, in the context of MOND, there is a natural way to choose the interaction, because MOND revolves around accelerations. And in general relativity, it's not possible to define a sensible acceleration, because what would be gravitational acceleration in general relativity would be embodied in the Christoffel symbol, in the connection. But the connection is not a tensor, of course, so we cannot construct scalars from it, which we would need to construct a theory. But when you have two metrics, so you have two connections, it's well known that the difference between them is a tensor, so you can construct scalars out of it. And certainly in the context of MOND, where acceleration is, where you have a naught, it gives you natural means to construct such scalars. So, for example, with the right units, C, which is the difference between the Levi-Civita connection of the two metrics, C has dimensions of acceleration, so this is a dimensionless tensor, and you can construct scalars from it, and you can use them as arguments for this interaction. So one choice of scalar that I found particularly happy is to take this combination of indices, which is essentially the same as appears in the Ricci scalar. Okay, the Ricci scalar also has derivative part, so derivative of the connection, but as some of you probably know, it's not really necessary in the action. Did you signal me? Because I didn't notice. So how much time then?
Well, we're up, so why don't you try to
Okay, very quickly. Okay, so some nice features about the theory. It has, at high acceleration, it goes to general relativity, so you don't have to worry about solar system tests. In the solar systems, acceleration are very high, so it corresponds to this limit, and so it's you just get everything. Metric equality means if the two metrics are the same, if you have the system with two metrics being the same, then the interaction disappears and you just get two copies of general relativity, which is important for cosmology. It has a non-relativistic limit that is MOND, of course, with a single potential, so the phi and psi that appeared in some of the previous lectures are the same as they are in general relativity. So, for example, the prediction is that a cluster or galaxy would show the same effects on lensing and on massive particle motion as if it had the same dark matter halo or the same potential, essentially. No time to talk about this, other approaches, so I'll just in the summary, I just want to emphasize one or 2 points. So the first is that MOND is indeed still under construction. So there are many things that we don't understand about it. We're not completely happy with the theories, that certainly not with the relativistic theory. Even this relativistic theory that I just described is probably not final word. So, but, okay. Okay, there are symmetry aspects that I did not have time to consider, but it turns out that the theory in the deep MOND limit has the same symmetry as the isometry of the Ceter space, and that is another connection with cosmology. So one is that A naught in value is connected with the radius of the de Sitter. The other is that symmetries of the deep MOND limit are identical to the isometry group of the Ceter space. Okay, I leave it to you to read the rest. Thank you.
Your point on the last slide, replacing cosmological dark structure, some preliminary work. The cosmological dark matter is needed to seed the growth of structure. So how do you play that role in MOND?
Okay, it's actually MOND certainly has unique aspects that are also conducive to the one reason you need dark matter in cosmology is to enhance galaxy the collapse of structure. Okay, and that certainly works in MOND as well. I didn't have time to discuss it, but it's not that we have a theory that does what we need. But certainly there are, because structure formation is characterized by no acceleration in the context of MOND, certainly it is faster and effective than it is in standard dynamics without that. Whether you get exactly the correct. In fact, some preliminary attempts to get structure formation with MOND show that you get too much of structure formation. It is too effective in some sense. You have to stop it from forming too much structure too quickly, for example. So it's not that you don't have mechanisms you want to replace that method, but they may not be the right ones.
Yeah, I was curious about your BIMON theory. So how many degrees of freedom do you have in that theory?
Well, it has 20, of course.
Right.
And it has the same, only one diffeomorphism, so -4. 20 minus 4.
I see.
In general.
I see.
Those.
And is it stable? Are the modes propagating all?
Okay, it's interesting. Wave has not been considered in detail, but there's something very interesting that happens. Say I want to consider waves on the double Minkowski background, so I just expand G mu nu is eta mu nu plus H mu nu, and the same for the other metric. So it turns out that you should look at the sum of the two H mu nus and the difference. So for the sum, you get exactly general relativity, turns out. So you have, of course, all the gauges, the transformation that you can perform act only on H plus plus on the sum of them, because they are transformed in the same way, so that they don't act on the difference. And the sum, so you have at your disposal all the usual gauge transformations. So the sum of the two degrees of freedom behaves just like general relativity, moves with the speed of light, as the same second order action. The difference is non-propagating, it turns out, because it comes from the phenomenology of MOND requires that this interacting function should be non-analytic around double Minkowski background. It has to, because of this requirement, has to go like square, like a square root cell. And what happens is that this implies that the difference modes do not propagate, actually. So, like a miracle, but it's really imposed by phenomenology in the first place.
In terms of testing MOND in the solar system, there was some discussion about the Lagrange point. Is that an experiment that people are thinking about or not possible?
Well, it was routed as a possible application of LISA Pathfinder. I personally don't think that it is a test. What happens is that because MOND is non-linear, typically somewhere in the solar system you cannot detect any effects of MOND. So people suggested going not to the Lagrangian point where the centrifugal force is also involved, but to the saddle points where gravity of, let's say, the sun and the earth cancel each other. Now it has to be realized that the region where the acceleration is smaller than A naught is only about a meter in size. And it is, of course, it's not even stationary, it is rotating with the earth around the sun. But the suggestion was not, the suggestion was to send LISA Pathfinder after it finishes, if it is flown, and after it finishes its duties, to send it to near this point, and since it has sensitive accelerometer, but there's no way they can actually aim it to this 1 meter, so they will miss it by tens of kilometers. And at that distance, it depends on how fast MOND approaches Newtonian gravity in the limit of high accelerations. So for typical functions, I mean, I don't think they can measure anything.